What we're going to do today is we're going to discuss what nuclear chemistry is. We're going to first of all talk about what nuclear radiation. Nuclear radiation is where you're dealing with particles that are charged and that they emit energy from the nucleus of various different radioactive isotopes. And remember, isotope is a variation of the mass of an element. Okay, and the three types of nuclear radiation we're going to address are alpha, beta, and gamma. Okay, just to recap, let me get my pen on for here. What we have over here, of course, here's our symbol. When you see an atom written like this, the top number is always the mass. The bottom number over here is the atomic number. But in a periodic table block, remember, the symbol was written in the middle. You had your atomic number written on the top and your mass written on the bottom. But how they display it in this fashion, when you see the bigger number on top of the smaller number, always remember that the bigger number is always the mass. It is always bigger than the atomic number. Okay? Just to recap. All right, so let's start first of all with an alpha particle. And an alpha particle, remember, is going to be positively charged, and it's composed of 2 protons, 2 neutrons. And how you express it is written down here, just like what we just expressed. Has a mass of 4, has an atomic number 2, so 2 protons, and your mass would be 2 protons, 2 neutrons added together, give you that 4 up top, okay? Or it could be expressed as that little symbol, the alpha one. Now, it can be stopped by a thin sheet of paper, so this type of radiation is very minor in harming or hurting someone, okay? And as I said again, has a mass of 4 atomic mass units, AMUs, because of the 2 protons, 2 neutrons added together. Add those 2 together to get that mass of 4. Okay, now beta particle right here is negatively charged, okay, and it mainly consists just of those electrons, whereas the alpha particles lack the electrons, beta particles have those. It can be stopped by a piece of aluminum foil, so your Reynolds wrap that you buy from the grocery store or your aluminum foil you buy, that can stop beta particles. It's a little bit thicker, more dense than the sheet of paper. How we express it again, look at this right here. You have your atomic number, or as expressed like this, it will be the charge of -1 will be written on the bottom, and then you have the little e for that little electron for the beta particle, or just a B for beta. Okay, and it has a very small mass. Okay. Gamma radiation, again, is one that we used for people undergoing cancer treatments. It has the highest frequency that's found on that electromagnetic spectrum that we talked about. All this high energy is actually going through space on there. It has no mass, no charge, but it has a high energy. Now, to stop gamma rays, basically you could either, one, have a room composed of 3 meters of concrete, which is very thick, think 3-meter sticks, put together that deep, or 3 centimeters of lead. So people undergoing the radiation treatments where they're using gamma rays, the walls, the ceiling, the floors are all coated or used sealed with lead. And there's the symbol for gamma. All right, now we're going to go through different ones of these decays. Now, the first one with alpha decay, this is where you release, as a part of the example, you release your alpha particle right over here. And basically, remember, your mass is 4, and your atomic number or your protons are 2. So protons, this is protons and neutrons. And remember, this is 2 extra protons here. And so in order to have this decay, you start with uranium here. And we know we're going to end up with 4 protons and neutrons over here. So in order to find what that mystery element is right here, take 38 minus the 4, you get 234. And when you look up the element to find the element, you have to look up the atomic number. So we'll start here. The uranium is an atomic number of 92. We're going to subtract 2 from it to get 90. And element number 90 is actually thorium on there. Make sure that is correct. Yes, thorium is correct. Okay, now let's practice this. All right, so here we're having the alpha decay practice. Now, first of all, what we're going to do is put the 4 and the 2 over here in the helium. Remember, this is alpha decay. Okay, now we're going to take 210 and we're going to subtract 4 from it. So we get 206 as its mass. Now to find out what that mystery element is, we're going to take 84 and we're going to take 2 from it, so then we get element 82. Now I got to go to my periodic table to find out atomic number 82. Atomic number 82, and I get lead, which is Pb. Okay? So again, 210. So in order to get 210, we take 206 plus 4, you get 210. And element 82 plus 2, you get 84. Okay? All right, now beta decay, you can see right here, is where a neutron decomposes to a proton and electron. The proton will stay, and the electron is actually released out. And so the mass number stays the same. You can see right here that your mass is staying the same, but your atomic number will increase by 1. Okay? Because 91 plus a negative 1 is actually 90. Okay? So let's practice this. Remember, over here in the beta decay, we're going to write the beta number, which is 0, negative 1, and we're going to put a little e. Now we're going to figure out what this element is. So your mass is actually going to stay the same. So we got 6 plus a negative 1 would actually be 7. Okay? And when I look up that, it is, element 7 is nitrogen. Okay? So 7 plus a negative 1 gives me 6. Okay? Remember, this one goes up by 1. Goes up by 1. Okay? All right. Now, let's talk about half-life. Half-life is the time it takes for half of an element or a sample to actually decay. Okay, so you can see on this line that we have over here, it shows half-life, half of it to decay, half of it to decay, half of it to decay, and so forth. A lot of math problems use half-life situations. So here we have an example of half-life practice. So we have a 30-gram sample of radium-226. And it has a half-life of 1,620 years. How many years will it take to only have 7.5 grams? So, let's start here. Let me show you my little shortcut. What I do is, first of all, I'm going to put 30 grams of that substance. So we want to know how many grams to get to 7.5. So first of all, what I'm going to do is take half of 30. What's half of 30? So 30 divided by 2, I get 15 grams. Okay? So we just start taking half of it. So to go from this step to this step is 1,620 years. So to go from 30 grams to 15 grams, whoa, it took 1,620 years, okay? Now, keep going because that's not the 7.5 grams that we want. So we want half of 15, and half of 15 is that number we want, 7.5. 7.5 grams, all right. But to go from 15 to 7.5, again, we went through 1,620, okay, 1,620 years. Now, to know how many years total, just add up how many times you did this, okay? So I get 0, 4, 2 plus 2 is 4, 6 and 6 is 12, carry the 1, and add that up. So it took 3,240 years. Now another way you could do it other than just adding these up, take 1,620 and multiply it times 2. We're doubling it, okay, on there. That's your half-life practice. So again, set it up for your grams to take the final decay. 30 to 15 is one step. 15 to 7.5 is another step. Okay, now what we have right here, there are two types of ways that nuclear reactions can occur. One of them is by fission and one of them is by fusion. Okay, fission is what we typically occur on Earth in nuclear reactors, and this is where we're going to take an atom and we're going to split the nucleus into two smaller particles. It's almost like tearing it apart to get the energy out. Okay, so that's fission. Think of the word splitting for fission. Now the other one that's seen on the sun and in stars is actually fusion. And I think of bones healing together, a broken bone will fuse together, and this is where they're going to mesh or combine together, okay? And it's going to produce a lot of energy, okay? So they fuse together, they combine is the key word there. They're combining together, okay? So fission, you're tearing it apart. Fusion, you're putting it together, okay? Any questions? Okay.